In this video, we look at the AC power in time domain, and then we look at the power in phasor domain, which means the complex domain. In time domain, we describe the power by instantaneous power. P of t equals V of t multiplied by I of t. This instantaneous power is changing with time. Next, we want to look at the average power, which is a time averaged instantaneous power. We take P of t, we do integral from 0 to t, and take the average over the time t. And this t is the period of the instantaneous power. This average power is a number. It's a real number. It can be positive, it can be negative, but it does not have complex part. The relationship of average power with the complex domain is the real part of V multiplied by conjugate I, and take the half and take the real part. Phasor V equals to Vm theta V, and I equals to Im theta I. And the I conjugate, that's Im minus theta I. You reverse the angle for conjugation there. Let's introduce the phasor of RMS values. So VRMS equals to Vm divided by square root 2, the same angle of theta V, because the RMS value for the sinusoid is Vm, the magnitude divided by square root 2. That equals to VRM, yes, angle at theta I. And the same thing of current IRMS, that's phasor, that equals to Im, that's the magnitude of the current divided by square root 2, the same angle of theta I, that equals to IRMS and theta I. So pay attention to the notation here. The bolded upper letter is phasor, is complex number. This is bolded, and this bolded is complex number. An uppercase unbolded, normally that's the magnitude, that's a real number. This is uppercase, but not bolded, this is a magnitude. The same thing here. This is a magnitude of RMS values. Next, let's introduce the complex power. Yes, big yes, bolded, VRMS multiplied by the conjugate of IRMS. This equals to half V multiplied by I. These are all in phasor domain. These are complex. The unit of complex power is V of A, volt in amp, because that's a voltage multiplied by the current. So that's V of A or kVA, depending on the quantity. Next, let's introduce different terminology of power, which means apparent power, real power, and reactive power. And all of this sounds very overwhelming. But if we look at the expression of complex numbers, they are all related with polar form and rectangular form. So we try to relate the expression of complex numbers and the physical meaning of the power. So in that way, hopefully it will help us understand different meaning of the power. Let's introduce apparent power. So what is apparent power? That's the magnitude of complex power. If we recall that's this complex power, this is the complex number we can write in the polar form. So magnitude of S, this is complex. Magnitude of S, and theta is theta V minus theta I here. See, this is a big capitalized S. This is capitalized but not bolded S. So this is the magnitude. Apparent power, that's yes. The unit is VA kVA. So that's the magnitude of complex power, and that equals to magnitude of VRMS multiplied by IRMS, or half of the magnitude of VM multiplied by IM. The physical meaning of apparent power is what is the power that circuit seems to have. The unit is measured by VA. This is to distinguish it from the average power, our real power. Next, let's introduce the real power and reactive power. In this case, the complex power is expressed by the rectangular form. This is a complex power. is equals to P plus JQ. And P is the real power. That's also the real part of the complex power. It is also the average power. So real power, the real part of the complex power, or the average power, those are the same thing. The reactive power, that's the imaginary part of the complex power. The unit is VAR, so volt amp reactive. If we look at the complex power, this is one expression, S equals to half V conjugate I. Using the Ohm's law in the phasor domain, we can express the complex power as a function of the impedance. The complex power is equals to half Im squared Z or RMS squared multiplied by Z, or the complex power equals to half Vm squared divided by Z conjugate. That equals to V RMS squared divided by the Z conjugate. So this is one relationship, and this is one relationship. This is a one. This is the same as this, and this is the same as this. Either way, if we know this, we use Ohm's law, we can derive all of this. Let's memorize one of them. We memorize S equals to half Im squared multiplied by Z. Now we recall the impedance Z equals to R plus GX. R is the resistance, and we can see that P is the real part. That equals to I Rm squared multiplied by R, and Q equals to I RMS squared multiplied by X. Q depends on the reactance, therefore the name reactive power. Next, let's introduce the concept of power factor. Power factor is a very important concept in AC circuit. It is defined as a ratio of the real power and the apparent power. Real power is also average power, that's this expression. And apparent power, that's this expression. If we take a ratio of that, that equals cosine theta V minus theta I, that equals cosine theta. Now let's look at a couple of special cases. If theta equals 0, which means theta V and theta I are in phase, they are equal. So theta V equals theta I. So the power factor equals to 1. In this case, the apparent power S equals to P. P is the real power, which means the Q equals 0. There's no reactive power. In this case, the circuit is a pure resistance circuit. If the power factor is 0, in this case, the apparent power equals to Q, the Q. The apparent power is imaginary, so there's no real part. In this case, the circuit only contains inductors or capacitors. There's no resistance to consume the power. So the power is stored by the inductors or capacitor, and then it is released by the inductors or capacitors. Next, let's look at the three factors. The sum of the imaginary part of the complex power, which is the sum of the reactive power, the phase of the current related with the voltage. If the phase of the current leads the voltage, we say the circuit is leading, otherwise it's lagging, and also the circuit load. So if Q equals 0, that's this case. If Q equals 0, the power factor equals to 1, that's resistance load. Let's recall this relationship. S equals half Im squared multiplied by Z. From this relationship, we can see the real part of the complex power has the same sum of the real part of the impedance. The imaginary part of the complex power has the same sum of the impedance. Now, if Q greater than 0, which means X is greater than 0, it is inductive load. because Z contains inductor component, which is J omega L. In this case, the current lagging the voltage because inductor circuit current lag voltage. If Q less than 0, the impedance contains negative J component, which is a capacitor load. In this case, the current leads voltage. In practice, the utility companies for electricity monitor the power factors very closely. They also pay attention if the power factor is a resistor load or the capacitor load. They may perform the power factor corrections according to their need. The company also references the power factor to set up the utility bills for the consumers.